Welcome to a lesson with Dr. Powell. Let's look at an example of how we can find the component of one vector along another one using complex multiplication. Okay, so let's suppose we have one vector and we're going to cast it down here. We want to compute these values. All right, so let's do that in an example. Okay, suppose right now that this point has now in vector notation, I'm going to use this for like tip because, okay, so instead of parentheses, I'm going to use this is like the tip of a vector. So suppose that this is like 3, 1, and suppose then that this is maybe like 2, 2. Okay, so we're going to concentrate on taking this vector and casting it down here. How are we going to do it? Well, this vector right here, think of it as 2 plus 2i. This one is like 3 plus I. Take the complex conjugate of this one. That's the vector that looks like this down here, 3 minus I. And we're going to multiply that to this guy up here, and it'll rotate this picture so this length, this 3, 1 will actually be on the ground now, and then this one will have this angle above the ground as desired. So we have 2 plus 2i, and let's multiply it by 3 minus I. Let's see. Okay, and then the real part of this multiplication will give us this L1, except for it's been expanded, so then we have to divide. What do we divide by? We divide by the length of 3 plus I, which is the same as the length of 3 minus I. How do you get the length of this? Well, just think Pythagorean theorem. And this is like 3 this way and 1 up, right? So, so the length is, well, we just take 3 squared plus 1 squared, and then we get to take a square root. So 9 plus 1 is 10, so square root of 10. So we're going to be dividing by the square root of 10 as we go. So L1 is going to be something divided by the square root of 10, and that simply is going to be the real part of this multiplication. To get the real part of this multiplication is not too bad. All you just have to avoid in the multiplication anything that would give you an I. That only comes from the OI part of the FOIL. Okay, that would be the imaginary part. So this is like outside parts and inside parts of the FOIL process. That would give you imaginary. We don't want that. What we want for the for L1, it's actually F plus L always. So it's the F plus L of this complex multiplication. So we get 2 times, so we get right here, we get 2 times 3, and we get 2i times negative I. So that's what we're going to get here. So we're going to get 2 times 3 is 6, and 2i times negative I. So I times I is negative 1, but then there's a negative, so it becomes a positive 1, so we just get 2. So plus 2, all over square root of 10. So we end up getting 8 over the square root of 10. And that would be our L1. Now L2 is not too bad. We can do that one really. L2 also, again, we're going to be dividing by the same expansion factor to get back out of the expansion that we had to do when we rotated the picture down. So then for that part, we do the imaginary part here, which is the OI. Okay, so 2 times, and we're only going to look at the coefficient of I. That's the part that we need for the length there, for that distance. So we look at the coefficient. So let's just look at coefficients. 2 times negative I has a coefficient of negative 2. So I'm just going to write that down, negative 2. And then we have 2i times 3 has a coefficient of 6. So we have a plus 6. So notice that L2 would simply be 4 over root 10. So we get L2 is equal to 4 over root 10, and L1 is equal to 8 over root 10 in this picture. So we're able to find those component lengths simply by using complex multiplication. Thanks for watching.